Alright, so what we have over here is we have our balanced equation for the combustion of hexane. And if you want to see how we balance this equation, there should be a video on that on our channel that we posted before. And what this balanced equation allows us to do is it allows us to figure out, given a certain amount of reactant, how much product we get. And what do I mean by that? Well, if we go back to our ham and cheese sandwich example that I talked about in our last video, if I were to write a balanced equation for making a ham and cheese sandwich, it looks something like this. It looked something like this. 2 pieces of bread plus a slice of ham plus a slice of cheese yields us with a ham and cheese sandwich. This is a balanced equation for making a ham and cheese sandwich. And what I can do here is I can say, well, if I had 4 pieces of bread, right? It takes 2 pieces of bread to make a ham and cheese sandwich, so I can make 2 ham and cheese sandwiches. But what if I had 4 pieces of bread and I only had 1 piece of cheese? Well, if we went by the number of how much bread we have, we could say, oh, we can make 2 ham and cheese sandwiches, but we only have 1 slice of cheese. So that limits us from making 2 ham and cheese sandwiches. We can only make 1 ham and cheese sandwich. Because I can't make a ham and cheese sandwich without a slice of cheese. That would just be a ham sandwich. And I don't want a ham sandwich. I want a ham and cheese sandwich. So the cheese in this situation is what we call our limiting reagent. Our limiting reagent. It limits us from making as much product as we can. So, let's say, I'll go ahead and erase this out of the way. Let's say we had a situation where we want to figure out how much carbon dioxide, how much CO2, right, is produced when we react, let's say, 200 grams of hexane, hexane being the molecule on the far left, C6H12, with 500 grams of molecular oxygen, of O2. Well, the first step here, the first step would be to make sure we have a balanced equation. We do in this situation. Again, if you want to see how we balance this, we already uploaded a video on that. But our second step here would be to figure out which one of these, hexane or molecular oxygen, is our limiting reagent. Well, obviously we have less hexane in just pure weight than we do oxygen, but we don't like to compare separate molecules based off of their weight in grams. What we do is we compare them using moles. 6.02 times 10 to the 23rd atoms is equal to 1 mole. So we need to figure out how much moles of each of these we have. Well, to do that, we need to figure out the molecular weight of each one of these molecules. So, for hexane, hexane is, if we take a look at our periodic table, 1 mole of carbon is 12 grams per mole. If we multiply 12 by 6 and add 14 to it, because hydrogen is about 1 gram per mole, we end up with hexane being about 86 grams per mole. For a mole of hexane, a mole of hexane is 86 grams. Now for oxygen, for molecular oxygen, 1 mole of oxygen is 16 grams. So multiply that by 2 and we get 32 grams per mole. 32 grams per mole for molecular oxygen. So now we can figure out how many moles of each of these we have. If we go ahead and we take the amount of grams of hexane, we have 200, and divide that by 86, we get about 2.33 moles. So I'll write that to our left. We have 2.33 moles of hexane. Alright, and if we did the same for oxygen over here, we have 500 grams of oxygen. Divide that by 32, we end up with about 15.63 moles of oxygen. So I'll write that over here, 15.63 moles of molecular oxygen. I'll go ahead and erase this over here so that we don't get overwhelmed. Alright, so now we know how much moles, or how many moles of each molecule we have. So which one of these is our limiting reagent? Well, we want to be careful. We might want to jump and say, oh, there's less moles of hexane than there are moles of oxygen, so hexane has to be our limiting reagent. Well, we have to be careful because we have to look at our balanced equation over here, right? Our balanced equation over here. Our balanced equation says that in this equation, in this reaction, 2 moles of hexane react with 19 moles of molecular oxygen. That's a lot of oxygen per hexane, right? So how we can figure out which one is our limiting reagent is to set up a ratio. Okay, so 19 moles of molecular oxygen is needed to react with 2 moles of hexane. And if we make that a fraction, that's about 9.5. So 9.5 moles of oxygen per mole of hexane. So let's make a ratio using the moles we were given. So 15.63 moles of O2, 15.63 moles of O2 over 2.33 moles of hexane gives us, one second, about 6.7 moles of oxygen per mole of hexane, and that is actually less than the ratio given by our equation. So with that, we know that that oxygen in this case is actually our limiting reagent. Another way we can go through this is by dividing the amount of moles we have by their respective coefficient in the equation. So 2.33 over 2 will give us an answer a little bit over 1. It'll be about 1.2. And 15.63 over 19, well, that's going to give us an answer less than 1, right? That's going to give us about 0.8. So again, here we see that oxygen is the limiting reagent in this equation. Even another way to go through this is to just use these moles and go through the equation and figure out which ants, or with these moles, which one produces less product, and that will be your limiting reagent. So there's a lot of ways to figure out which one's the limiting reagent. I find setting up a ratio and figuring out if the ratio of these moles is less than or greater than the ratio of the respective coefficients, and using that to figure out which one is our limiting reagent. But here we figured out that oxygen is our limiting reagent. So that means we have to go by the amount of moles of oxygen we get to figure out how much product we get, and in this case, figure out how much carbon dioxide we get. And that makes sense if we go back to our ham and cheese example. If we had 4 slices of bread and 50 slices of cheese, let's say, we can't say, oh, we have 50 slices of cheese, we can make 50 ham and cheese sandwiches. No, we have to go by the fact that we have 4 pieces of bread. And with that, we can conclude that we can only make 2 ham and cheese sandwiches. So we have to go by the amount of oxygen we have in moles. And how can we figure out how much CO2 is produced by 15.63 moles of oxygen? Well, again, we can set up a ratio. So for 19 moles, going off of our equation, 19 moles of O2 gives us 12 moles of CO2. And we can say that's equal to 15.63 moles of O2 over, I'll just say X, with X being the moles of CO2 we have. So we can go ahead and we can cross multiply, giving us 19x being equal to 12 times 15.63, about 187.56. Divide both sides by 19, and we get x being equal to 9.87 moles of CO2. And I'll go ahead and write that over here. So 9.87 moles of CO2. So with the information given, we know that we get about 9.87 moles of CO2. Now, if we were asked how the weight of CO2 that would be produced with this information, the amount of grams of CO2 is produced in this equation, well, we need to figure out the molecular, or the weight for CO2, right? So carbon, again, is 12 grams per mole, plus 2 oxygen, which oxygen is 16 grams per mole, so plus 32. So we know there are 44 grams per mole of CO2. And if there's 9.87 moles of CO2, then we just need to multiply that by 9.87. I can go ahead and show it like this. There's 44 grams per mole of CO2. We know there's 9.87 moles of CO2. Go ahead, these cancel. So 44 times 9.87 gives us about 434.28 grams of CO2. So, after all of that, we know that given 500 grams of oxygen and 200 grams of hexane, when those react together, we get 434.28 grams of CO2.